Okay, so
WHIM.
no, this one I have. Just yeah.
So,
So the thing is, this is an exercise with the solutions are already there. So
where is the?
yeah, so the data that you have in the disk, the images, the 2W, TW Hydra, yeah. These are the final products of the analysis. So here you have the channel images and the moment maps. And you have it for two lines, for the CO32 and for another lines, HCO plus. Okay, so there are like two data sets there. For the same band 7 data of TW Hydra, in that range, you can detect two lines. So they made a data cube for the CO line and another data cube for the HCO plus. So you have the channel maps, and what they have done is to create moment maps. Okay. The idea, the exercise is that you yourself try to go from the channel maps to the moment maps, the same way as they did. Those steps are all in the CASA guide. I will put it now, and perhaps we can do it some steps together. But the idea is that you learn to visualize that data, and you calculate the moments the same way they did. And you can also take a look to the paper that I mentioned in the exercises. There you can see in a scientific paper how do they show the images and what is the analysis that they do there. So they basically try to model the kinematics of this disk, yeah, with different kind of with three models, and then they discuss. So the idea is that you generate the same kind of plots from that data set, from the data cube. So the data cube is one image per channel, so per velocity. And the idea is that to get the moment zero map, the moments of the data cube are basically the moment zero map, which it's telling you the distribution of the gas, because you are collapsing all the channel maps. You are collapsing them all you are integrating along the velocity axis, so you collapse them, and you have a map of the distribution of the gas. Then you have the first moment map, which is the average velocity, okay? And then you have the third moment map, which is the velocity dispersion. So you have the gas, like if you, okay. So you have like, so you have slices, which are the channel maps, and then you collapse it along the velocity axis to see. The first one is where is the gas located. The second one is which velocity has this gas, and the third one is the velocity dispersion of this gas. This is basically what you need to get from this data cube. So yeah, before the break, we were just learning how to display these results. Now that you know how to take a look to the channel maps and moment maps, the idea is that you take the channel maps, and calculate the moments yourself. And the result should be similar to the ones that you already have. And so for that, if you go to the TW Hydra, to the guides,
This one.
yes, this guy, if you scroll down. So this is the images that I want you to obtain from the data cube. Okay. In order to get to this point, if you go, they have different steps. So first they have the calibration step. We will not do that. If you want, you can do that. We will do this step for another target on Monday. But if you wanted to do that, you just download the data, the raw data, and follow the steps there to get the calibrated data. Then once the data is calibrated, then you image. So then you would be doing what we were doing yesterday with AbsynSim. You will doing the same to obtain the final images. And then when you obtain the final images, this is the data cube that you have there, you do the analysis. And that analysis is what goes in the paper, if you ever find something interesting. So in the paper is the analysis part. And what I want you to do is to follow the, if you go back to the, it's okay.
Yeah.
You go to the imaging here. Yes, yes. There it explains how to obtain the images and the data analysis. I think it's down there, right? Like, okay. And I think even in the exercises part, I wrote, you don't have?
No.
Ah, I thought.
The slides are not in the website.
Oh, damn it! I thought you were only missing the moment maps.
No.
I'm going to write an email now to Jorge. Sorry, I didn't understand. Too bad. I thought it was. I understood that you were just missing the moment maps, not the rest.
Yeah.
Too bad. Sorry. Okay. My
It's
apologies.
The web page is slow.
Yeah. Okay, I see. But everybody or? Oh, okay. Yes, so you have it here. Good. So here it's telling you how to go from the calibrated data, from the visibilities. So you have the visibilities. It's telling you, it's explaining you how to get to the image, how to do the convolution process. And once you can take a look. We will do the same on Monday with this. If you want to do it with this dataset, it's okay. We can do it with another one. Once you have the visibilities, then here is where it does the imaging. You can click there. Yeah. So basically, it's taking the visibilities and it's subtracting the continuum first. So because you have, you don't only have the line there, you also have a continuum. The continuum is brightness in all the frequencies. So you basically, Alan was showing you that you have a continuum and then on top of it you have the line. So this step is to remove the contribution of the continuum. And then you only end up with the line. This is it's doing the continuum subtracting. You can go. Then it does clean. It does the imaging. This is what we were doing with AppSimSim. We had the calibrated visibilities, and then we were doing the imaging. So here you can see all these parameters that I was explaining you yesterday or the day before, I don't remember, no, yesterday, with the clean algorithm. You have the imager mode. This is the algorithm that you are choosing. You could do the multi-scale that we were talking about. This is the CS clean. Then you are choosing the image size as well and the cell size. So these are the two parameters that I was trying to explain you yesterday that are very important, and it's up to the user to select. So here they chose these two, image size and cell size. They want the axis, the frequency axis to be expressed in velocity. You could have it in frequency. It's just by convenience. You choose the velocity. And here it's choosing at which velocity to start and which resolution, velocity resolution I want to make an image. So the resolution along the velocity axis. Okay, this is the risk frequency of your line. So the CO line, the CO2, 3 or 3, 2, whatever, has this risk frequency. So I will be using, this is you will learn it later. Depending if the target is a galactic source or an extragalactic source, we use a different velocity frame. So this is the velocity frame that we use for galactic objects. This is the weighting I was talking about. Here is making a choice of robust 0.5, which is a positive robust that goes a bit towards the natural weighting. And then, this is interactive. Interactive true means that you will have to choose manually which boxes do you want to, clean boxes do you want to select. So it will show you the dirty image, and then you have to select the box where you want to clean the data. If you put interactive false, it will not show you anything, and it will just work in the background. So what we do first is perhaps you do a first attempt with not many iterations to check clean boxes, and then you run it again without interactive equal true, you put it in false and let it run for, because these data usually are big. And yeah, so here it has a threshold of 1 millijanskins, and you can see here that it has put a lot of iterations. So actually, they want to reach the sensitivity limit. So in this case, they leave a lot of components, and the cleaning algorithm will be stopped by the threshold. Okay, so if you scroll down, so it does this is the same as for the HCO plus line. And now this is what I want you to do, the analysis part. So in the previous step, they obtained channel maps, a data cube. And now, once you have the data cube, now what do you do? So this is the analysis part. This is what goes into the papers. So I want you to take a look to the data cube and make a position velocity diagram, which is a cut of the data cube along a certain axis of the source. And then you can see in velocity, what is the velocity of the gas along that axis? Okay, so this is the one thing I would like you to do. And then the other thing is obtaining the moments. In the folder that I just shared with you, you already have the solutions to this exercise. So it's not, I'm not asking you, you could do, you could already use those moments if you wish, but the idea is that you learn how to calculate those moments. So if you follow, if you go down, you scroll down a bit more. So you can do all these CASA tasks, these CASA commands, to obtain the moments the same way they did. And you can do that yourself if you want. Of course, you can already grab the ones that are there, and I just give answers to my questions. So actually, I think I'm only asking you to upload the PV diagram. The rest is up to you to learn to play how to obtain the moments. So if you scroll down, it's telling you, okay, you can start, as we already did, by viewing how is the data cube and playing with the channel maps. You can actually calculate there which is the RMS, which is the noise in your images. We can do that together. I will do it in my laptop. Because what we do for calculating the RMS in the channel maps, you go to channels that don't have a line, and then you select a box not outside the center, and then you calculate the statistics, and then you see there what is the noise of a channel map that has no signal and has been cleaned normally, right? So this is what you do. And that level, that RMS level that you are measuring, it's used later in order to display the channel maps in the paper. Because in the paper, what you do is you measure the RMS in the line-free channels, and then the contours that you will show there will be powers of that RMS. So this is what it's done in the papers. Well, if you want to present scientific data, you have to be consistent with your noise levels. Okay, so if you scroll down, here is basically telling you how to visualize, I think, the targets. And here, if you go, it's telling you how to get a spectrum to the source. So there is in the viewer a tool called spectral tool, and then you can select a box in the channel maps, and it's going to open an extra window which is going to tell you how much flux is there in every channel in that area that you selected. Okay, so this is the profile, the line profile. So then you can see, when you have the line profile, you can overplot where is the rest frequency of the CO line to see, okay, this detection is consistent with the CO. And so it's going to tell you at which velocity do you have that gas. basically. So you can use the spectral tool in the on the channel maps to see that spectrum. If you scroll down a bit more,
What does the spectral map shows? It shows the flux per pixel.
so what does the spectral tool is you select a region, and then it goes to channel number 1. It integrates the flux in that region, and that number it puts into the profile in the velocity 1 flux whatever. Goes to the other channel map, integrates the flux in that area that you selected, measures the flux, and puts another point in the profile. So it does this channel per channel, and that's why you have this profile. So if you have in every channel, how much flux do you have in the region that you selected? And this is a way, when you first image a target that you have never seen before, you don't know where the gas is. Of course, you expect, if you know that that galaxy is traveling at a certain redshift with respect to us, you make a data cube around that velocity, and then you make a channel map, and you open the spectral tool. You select the region where you more or less expect where the target is, because sometimes when you put play to the channel maps, you already see the gas. But sometimes it's so weak that you don't see it very well. If it's just 3 times or 4 times the RMS, you really have to be very knowing really what you are looking for. So what you do is you select an area where you expect, according to the size of the galaxy and the coordinates, you select that area and you calculate the spectrum. And if there is some gas there, you will see a peak in the channel maps where you have some gas. And then you go to those channel maps and you see if the detection is real, is the gas is there or what. And then you calculate the moments, only restricting the velocity axis to those channel maps. Okay? So this...
And the width for the peak.
The width.
Yeah. Let's say you have this peak.
Yes.
So I know for this frequency, it's a frequency. Channels
Yeah,
are
yeah.
frequency.
Channels is frequency. It's, yeah.
Okay.
It's
so
velocity.
for this frequency is the maximum. And, but the width, which one is the?
No. So the source has this width. It's the profile.
I mean the range, the channels. Which one is the best option for the?
Okay, there are several ways to measure the flux profile, but what it's basically. There is an agreement among the astronomers, let's say, because this is an interferometer, so you have spatial information on where the gas is located. You can see it very well, right? But when you are using a single dish, you don't have this spatial information. You are just integrating already all the flux that is in that region. So for single dish observations, what you basically get is already the profile, right? For single dish, you just have flux for every velocity, for every channel, for every frequency. This is what you get with a single dish. Here, with this spectral tool, what we are doing is integrating in the spatial coordinates to get that point at every velocity. Okay? And you can choose in your map to make that region larger or smaller. But with a single dish, you just have your beam, and you are integrating in the beam area. Okay? So this is the profile that you would get with a single dish, and this is the profile that you are getting when you are using the spectral tool. What people how people usually measure the flux, first they do the total flux, which is the zero moment. It integrates all this area. And then they also give the peak flux, okay, which is telling you, yeah, what is my the peak of the line with respect to the RMS. And then to measure the width, what do they do is, okay, I measure the peak and I take half width, okay, half full width, half maximum. Yeah. So then they go to the 50% of the peak, and then they find, they measure this is the line width. This is the way that that you do to measure the line width. You go to the peak, and then you see, okay, at the size of the profile, which is the line width that I get. For very bright sources, this is quite clear. For weak sources, when the profile is down there, it's a bit tricky. But yeah, you can measure it this way. But yeah, in this, for the moment calculations that we are going to do, you basically see in the spectral from where to where, in which velocity range do I have to work to collapse these flags to get the total map and the velocity map. Because if I start adding extra channels here, I might end up adding only noise. So your map distribution will be much noisier. So you want to restrict your moments to the area of interest. Okay, so in the case there, I think they have the channel maps, and then in order to calculate the moments down there. Yeah, this is the imaging. Yeah, you can keep going. And there, you keep going down there. Make moment maps. Okay, here, it's making already the first moment, the moment 0, which is the distribution of the gas. So when you make the moment 0, you see where the gas is located in the disk. So perhaps you have a ring, perhaps you have a concentration of gas in the center. It's a bit tricky to see it only from the channel maps. That's why you collapse all of it. And that's why where all these beautiful disk images come from. The TW Hydra, the HL Tau image, all those disk images come from collapsing the channel maps this way. And here you can see that they made a selection of integrating only from channels 30 to 90, basically. So you check first what is the flags, and then you make the channel map. Here I think they just put you a way to nicely plot and already making contours of it. Okay. And then, yeah, if you go down, then it also makes how to estimate the noise, I think, in the moment map, and then it makes the higher moments. So now it's making the first order and the second order. So this is basically how you get you end up with these three beautiful disk images. Okay. So you don't have the exercise slides. Okay, I'm going to ask them to upload it. And yeah, have you? Have you tried to open other targets, other images, or just, okay. I'm going to first ask them to put the new slides, because otherwise you don't see the exercise, so you don't know. Sorry. That's too bad. Oh, so bad. images, so in the folder TW Hydra that it's in the images that you are looking at, they are already done. You don't need to image again. So you can use those images already for making the analysis part. But we were copying in all the computers also the calibrated data, the visibilities. So you could do also the previous step of making the images running clean on that data. And I think there is a folder called the calibrated data in the, yes, there. So here you have the calibrated data of TW Hydra. You could uncompress that and run the cleaning steps on that data. Okay, so that was the idea for Monday. But if you are like super willing to do that already, go ahead. So yeah, just the data analysis you can use. You can choose. You can use the data the images that are already placed there, or you can be brave and decide to run the cleaning steps.